Hey all, doing Codeforces Round 739, Div 3, starting 1 or 2 minutes late, so that's really bad for penalty, but let's just give it a go. Yeah, I guess that works. More than k different digits. I got TLE. Oh wow. Okay, well, that's annoying. Okay, that's worse. This will be faster. Oh, yeah, that should be okay, I think. I have horrible penalties, so whatever. Oh. Okay, I'm in first right now, but I have horrible penalties, so let's see. I see. Okay, so yeah, so you look at the end and you just I guess it has to be a factor of oh, that is good. Yeah, okay, so Order the letters by last occurrence. Okay, yeah, and then you can so we're actually going to sort how do I want to do this? So basically, so we have the order of all the characters. Oh, frequency. So it should be frequency of last. Okay, currently in 4th place. How many people could pass us? Actually, it's only Colin. Pretty sure. So if you were to get it now, that would be 35 penalty, which adds up to 110. So he has about 5 minutes to pass me. But I think regardless, should be top 5. And yeah, I guess I started slightly late, but that actually didn't really affect my rank too much. Okay, we can go through each of the problems here. Yeah, it looks like it ends with quite a few hard problems. E and F, not getting too many solves here. Although F1 is easier because you can try every number. So I actually expect F1 to have more solves than E in the end. Yeah. Okay. So let's just talk about each of these briefly. So problem A, Polycarp doesn't like integers divisible by 3 or ending with 3. And he writes out the list of all the numbers he likes and output the kth element of this list. And k is only up to 1,000. So what I do here is actually pretty simple. I just build the list in advance. I go up to 10,000 and I make sure it's not divisible by 3 and it doesn't end with the 3. And yeah, you would just want to make sure that your sequence that you build here is long enough. Mine is about 6,000, so it's plenty long enough. And yeah, ultimately we just read in k and we output the kth element of the sequence. So super simple. Yeah, not much to this problem other than that. Okay, problem B. You've got a circle arrangement like this. There's an even number of people in the circle, and they set up like this. You're told that person numbered A is looking at person numbered B. So for example, 1's looking at 4, or 3's looking at 6. And you want to know what's the number associated with the person number C. If there's no circle for A, B, and C, output -1. Okay, so basically what we notice is that, for example, 1 and 4, 2 and 5, 3 and 6, their difference is always the same, and it's always n over 2. So we can kind of pull n from that. So we take, yeah, n equals 2 times the absolute value of A minus B. And we also need, to check that basically one of A and B is between 1 and n over 2, and one of them is between n over 2 and n. And yeah, we just check that here. If they're, I guess it's mostly if they're both over n over 2, then we fail and we print -1. And then also if C is greater than n, we need to print -1. Otherwise we just check whether C is at most n over 2, and if so we add n over 2. And if it's greater than n over 2, we need to subtract n over 2. And that is the person C is looking at. Yeah, so not too bad, but a little tricky. You need to just make sure you handle all the -1 cases here. There is also this one, which is a little silly because A and B could be valid, but C could be too big. For example, if they gave you I guess they covered it here. They gave you 2 and 4, and they ask about 10. So that is covered by the samples. And then I guess I could have been more thorough and checked that like A and B are also not greater than n, but I think that's covered by this actually. Because if the bigger one is greater than n, then the difference, yeah, it just kind of works out. The difference is greater than n over 2, so it actually ends up being fine. Okay, problem C. So basically we're writing in a bunch of numbers like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And you're given a number, and you want to tell them where is this number, what are the row and column. And so the idea here is we're just going to group things by their kind of backwards L. And everything in the same backwards L has the same square root rounded up. So everything 5, 6, 7, 8, 9, if you take the square root and round up, you get 3. Everything 10, 11 through 16, if you take the square root and round up, you get 4. So first thing we do is we just do that. Take the square root, round up, and then I just take that minus 1. And difference is basically it's k minus y times y. K minus y squared. The reason for that is basically for the row, or not the row, but the section from 10 through 16. 10 will be 1, 11 will be 2, 12 will be 3, 13 will be 4, 14 will be 5, 15 will be 6, and 16 will be 7. And so that's what I'm working with now. There's 1, 2, 3, 4, 5, 6, 7. And then the idea is that the row is just the minimum of this difference and x. So 1 is here, 2, 3, 4, and then once you get past 4, 5, 6, 7, your row is still 4. And then your column is just x minus the max of diff minus x and 0. So in particular, if you're 1, 2, 3, 4, your column is just x. And then once you go past 4, every amount you go up beyond 4, your column decreases by 1. So that's why we take, we subtract diff minus x. So, you know, when diff is 5 and x is 4, we're subtracting 1 from the column. But if the diff is 4 or less, we're not subtracting anything. That's why it's max with 0. And that gives you the row and column, and we just output that. Yeah, it's good to kind of, if you're confused about this, it's good to just work through 10, 11, 12, 13, 14, 15, 16. And yeah, basically just try out all those, work through them, and make sure that it makes sense. And yeah, this is just O of 1 time, so obviously very fast. Okay, that's problem C. For problem D, we've got a number, and in one move we can do either of the following actions. We can erase any digit of the number, and you can actually make the number completely empty. And then another thing you can do is add 1 digit to the right. You can do these in any order, any number of times. And also note that if you delete a digit and it contains leading zeros, they do not get deleted. So if you delete 3 from 301, you end up with 01. And you've got to perform the minimum number of actions to make the number a power of 2. So basically for some k at least 0, that there is the result is equal to 2 to the k, and your number can't have leading zeros. So for example, 1052, you can add a digit 4, 10524, and then you can erase a 5, so you get 1024, which is 2 to the 10th. For 8888, you can just delete 3 of the 8s and end up with 8. So you want to know, yeah, the minimum number of operations. And you have 10 to the 4th test cases. Each one has n up to 10 to the 9th. So what I did here is basically, since there's only essentially at most 9 digits, I guess there could be 10 digits. Maybe I should test. Yeah, let me test my runtime on this. Is that too slow? Am I gonna fail this? I'm gonna fail this. That is dumb. Okay. Okay, that's too slow. I'm gonna have to do this. It's 2x too slow, I guess, which is That's really silly that there's one number that messes this up. I guess I'll just resubmit this. Okay, so yeah, I guess my solution, it must not be the best because they're oh, I guess what I can do, here's what I can do better. I can pre-compute for each power the answer, or for each prefix of power the answer. So here we go. So okay, so yeah, we'll have this, and then we don't need this, right? If oh, because the math lookups are slow. So I guess we need, is this better? It's a little better. Maybe we can avoid 2 to the 10th. And you can make a try. Oh, I know now. Yeah, I see. So this is, I see, this is not the best version of the solution. Okay, so the best version of the solution is to stick with the powers we had. Actually, we don't need powers at all. We can just generate them. And now we just greedy this for the amount we removed is and we need to add and this is where we get this is very fast. Okay. Okay, so this is a much better solution. Yeah, basically what we're going to do is we only need to consider powers of 2 up to 2 to the 60. And the reason for that is basically I'm going to claim that you never need more than 9 operations. There's 2 cases. One case is specifically 10 to the 9th. Specifically for 10 to the 9th, you remove all the zeros, and that takes 9 operations, and you end up with 1. For anything less than 10 to the 9th, you have at most 8 digits. You remove all the digits, and you add a 1, and that takes at most 9 operations. So basically, when you have 10 to the 9th, and you add something up to 10 to the 9th, and you add 9 more digits, you can end up with something around 10 to the 18th, and that's exactly what 2 to the 60 is. So that's why we don't need to go further than 60. Now, yeah, we're going to iterate every power of 2 from 2 to the 0 to 2 to the 60. And once we have that power of 2, we can kind of just greedy our way through the string. So we remove everything, or we just go through the string. And when we match to the next digit in the power of 2, we just keep it. The reason is we can only add to the right, so we need to match the left prefix, some left prefix perfectly. And this is just a greedy to find the longest matching prefix. And then, once we find that, the amount we have to remove from our original string is d, or the string size, minus the index, minus the number of matched characters we have. And then the amount we need to add is also the length of the power minus the number of matched characters. And that is our candidate. And that's it. So that is problem D. What I did earlier was more of basically I did a 2 to the D approach, where I considered all subsets of which characters I'm going to keep from the original string, and then you have to build that substring, and then you can do the greedy with an easier greedy even with the powers of 2. The problem is, yeah, TLE is definitely the problem with this approach. So made a couple resubmits there. But okay, just 2 more problems to talk about. Problem E. Yeah, so for problem E, basically, you start with a string, and then you basically concatenate copies of the string, but each time in between copies, you remove some letter entirely from the string. So you can get ABA, CABA, you remove B, and you get AA, CAA, and you add that. And then you remove A, and then you get C, and you add that. And we're given this T string, we need to figure out what S is. So, why does that keep happening? Okay, so, yeah, the main idea in my solution here is we can find the order of the characters based on when did they last occur in the string. So we find every last occurrence in the string, and then, we know the number of characters based on the number of distinct characters, and if, in one case, if, I guess this is no longer needed. Yeah, I can get rid of this actually. So, yeah, my code is not the shortest because, or it has some redundancies because I kind of changed to the idea halfway through. Okay, so yeah, so basically for every character in this order, it needs to occur a multiple of, if it is the ith character, it needs to occur a multiple of I+1 times, because it needs to occur 0, 1, 2, 3, all the way through I, and each of those has to have the same number of copies of that character. So that is one requirement for -1. And then once we find the number of occurrences, we can divide that by I+1, and that's how many times it occurs in the string s. So we can actually get the length of s this way by adding these up. Once we have the length of s, we know what, basically we know what the original string has to be, and we know what the order has to be, and we're just checking that it works. So we're building up what it should be, and we're just simulating the process here. So we add the string, and then we remove all copies of this character from the string. We check that they're equal, and then once they're equal, we're good. We take this string of order, and we take this original string again, and we just output those. I'll just resort this here. This shouldn't matter actually, I removed some slightly redundant code. Okay. Yeah, so that's E. The main idea is using the order of last occurrence is really good here, and the frequency is really important. And based on those frequencies and last occurrences, the order, we know how many times each character occurs in the original string. So we can just find the length of the original string, which means we take that prefix of t, and that must be the original string. And then all that's left is to just check that it works. In terms of runtime here, basically the runtime is linear in the length of t because when we're doing this process, we're basically building t, and so we basically, the amount of work we do is bounded by twice the length of t. Okay, and then lastly is problem F. I'll just talk about F2 since I kind of solved that directly and didn't really worry about F1. So in F2, you've got an integer n, and you want to find the minimum integer x such that x is at least n, and the number of x. The number x is k beautiful. What that means is, first of all, it has no leading zeros, and it contains no more than k different digits. So if k equals 2, then these numbers are all k beautiful, whereas these numbers are not. Yeah, so 10 to the 4th test cases, you're given n from 1 to 10 to the 9th, and you're given k from 1 to 10. So minimum k beautiful integer such that x is greater than or equal to n. Okay. Language server crash. Okay, so this is actually surprisingly short code. Basically, it's just a simple recursive algorithm. First of all, I try to keep the length of x the same as the length of n. If the length is not the same, then we only have two options. For example, if it's 2021 and we failed to find a number with the same length, then we're going to increase the length, right? So we'll have 5 digits, and the only options we have are 1, 0, 0, 0, 0, so 10,000, and also the number with all ones, 1, 1, 1, 1, 1. If k equals 1, we have to do the all ones. If k is at least 2, we can do 1, 0, 0, 0, 0. So we really only need to figure out if we can find a number with the same number of digits as n. Okay, so how do we do that? Well, that's just recursion here. We're going to start with the largest digit and then work our way down and build up the number as we go. So we're building from the highest digit down. So first of all, if the number of distinct digits is greater than k already, we already failed, so we return empty. And then the other thing is that if our current prefix of the number is already less than the original number, then we also failed, so we return empty. And then our last base case is once we've built every digit, we just return this number. And now finally, we just go through every digit from 0 through 9, try setting the next character to that digit, and recurse on index +1, and make sure to update distinct. Distinct just adds whether we did not find D in the prefix. And yeah, I mean, this recursion it's kind of a greedy order. It just tries the smallest number possible first, and just tries to fail things quickly. And yeah, if it doesn't find anything, returns empty string. So yeah, we just run that. This is the case that I described. If we can't find anything with this length, we have to go to the next length. I guess that case doesn't actually exist because you can just do all 9s. So yeah, so this should be fine. So we don't have to worry about that. And then, yeah, in terms of runtime, I mean, in terms of runtime, this should be pretty quick. I guess I don't have like a obvious bound on how quick it is, and I'm not. It's also not obvious that if this were up to 10 to the 18th, that it would still be super quick. But basically, you can think about. You can try this on a few numbers, and you can realize pretty quickly that it eliminates a lot of possibilities very quickly, and kind of ends up finding the right general range of number. So yeah, I know that's not a proof, but that is kind of the intuition here. Let me submit this version as well. I guess I could just submit to both. I know. Okay, but yeah, I mean, 46 milliseconds of runtime. And yeah, I mean, for this type of thing, you can also frequently just try it on a bunch of test cases. It is the type of problem though where there could be some weird test cases that take longer than others, but I do believe this should be a pretty fast solution, and it's also pretty short, which is nice. Okay, so that's it for all the problems on this contest. I guess my prediction of F1 having more solves than E is only slightly holding up, but contest is only halfway through, so we'll see what happens by the end. And yeah, those are the standings. My solution to D is probably TLE, so we'll see. I'll probably drop a decent amount, but anyway, that's it for now. If you like this video, feel free to like and subscribe, and I will see you in the next one.